Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Ladies and gentlemen, welcome back to another live stream. Okay, so let me share the stream with my server. Please join my server. You can find the link in the description so you can get notified of new streams and possibly vote on new streams. So, alright, live. Let's go. Alright, let's implement a generic static matrix in Rust. Alright, cool. So the chat is here, cool. Is the stream fine? Let me check. Seems good. The mic is on, camera is on, let's go. Alright, so I think we could start already. So today we're gonna be creating, well, a generic matrix in Rust. And it's going to be static. By static, I mean we're going to be using a two-dimensional array, not a vec. So it's not going to be allocated in the heap. It's going to be in the stack, you know. So though you may want to create a dynamic instead of a static matrix if you want the matrix to be big, very big, you know. For a stack matrix, like kinda, I don't know, maybe 5 by 5 matrix, or basically it shouldn't be too big, you know, otherwise you're gonna overflow the stack. But anyways, whatever. So in mathematics, a matrix is a rectangular array or table of numbers, symbols, or expressions arranged in rows and columns, which is used to represent a mathematical object or property of such an object. Okay, so let's start implementing this stuff. First of all, let's create a new library. Dash library matrix. There you go. New dash, oh, dash lib, okay. Matrix, and now let's go inside of the matrix. Okay, and let's just launch Visual Studio Code here. There you go. And now let's go. I don't need this trash, and I don't need this trash. And let's say, by the way, make sure to watch the other stream that I have done earlier, because I'm gonna be building on the knowledge I presented in that stream in this stream. So if you go to logs, like the previous, yeah, here you go, Rust Generic Programming Practical Guide. So I'm gonna be building on this stream. This is kind of like part 2 of the stream. So yeah. All right, hold on. There you go. It's in the chat. Great. Okay, so let's go and just do it. Allow did code and allow, what is the other one called? In used. Yeah, in used, right? And let's forbid in used must use. Now, just as a little introduction to mathematical matrices, if you don't know already. So I like this article right here. It's very interesting. But basically you have, let's say, a matrix of data, you know, it's like there's just, these are like column vectors, and then you have row vectors here, like a matrix of row vectors, and those row vectors are operations, those column vectors are data, and basically the data goes through all those operations and gets processed one by one, and then you get back your output essentially. So matrices basically just, it's like a fancy function, I guess. It just takes in data and spits out some transformed data. But anyways, so as you can see, like matrices can actually work in both, like in both contexts. Like it could be data or it could be operations, though nothing is stopping you from using a matrix that contains data as operations too. So it's kind of like programming and metaprogramming, like especially if you know Lua, like you have tables and meta tables. So like your table can be the meta table of another table. But anyways, whatever. So that's just something interesting there. Okay. All right, that's the first thing. The second thing that I'd like to show you is this guy right here, matrix multiplication XYZ. So you could here just do whatever dimension you want and stuff, and then you click on multiply, and this is how matrix multiplication happens. Okay, and you just go ahead. This is how you calculate it. And there you go, done. That's pretty cool. Let's go one another one, and there you go. Pretty cool stuff. Anyways, whatever. So let's just get started, I guess. All right, so let's make a matrix struct. And by the way, I forgot one little thing, which is our implementation wouldn't focus on performance, and in fact it wouldn't be anywhere near like other libraries, like for example NAlgebra. Like personally, I never really implement such stuff myself. I just use NAlgebra because, you know, it's just pretty much very involved. You know, there's just a lot of optimizations you can do, a lot of crazy stuff. So like if you check out this guy right here, if you go to source code, and let's just show you something here. Let's see, where's the geometry? Where's the matrix here? Let's see, matrix. Actually, let's go to NAlgebra documentation real quick. NAlgebra docs. Let's go, matrix. And if you go here, source code, and you can see that it's already quite crazy. So like it's generic, not just over T, R, and C, which is like the scalar, the rows and columns, but also on the storage, like is it static or dynamic, etc., etc. And there's just a lot of crazy stuff going on here, but whatever. Anyways, so let's just go to actually implement this step now. So struct matrix. So we're gonna need 3 generics. We're gonna need the scalar, and we're gonna need rows, const rows usize, and const columns usize. All right, now we're gonna actually use a 2D array. We're gonna use 2D array. So it's basically gonna be a scalar. Well, hold on. Here, like the outer array, like it's gonna basically be a 2D array, and the outer array would be rows, right? And like you could do this however you want. Like it's basically called either row column, like row major, I think, or a row major and column major, I guess. But anyways, let's just go ahead and go with scalar here and columns, I think. Okay, so columns and rows. So this is a 2D array. There you go. I don't really need the struct, honestly. I'm just gonna make it a tuple instead, or a tuple, depending on how you want spell it. But anyways, so now we got our matrix struct. So now we could make a matrix. Let's say matrix, and we could say like whatever, something like this. All right. Okay, what's going on here? Oh yeah. Let's make this an array. So our matrix, like you could implement this in a lot of ways, but in my case, I chose to make it a 2D array, right? So there you go, you just pass in a 2D array, and each of these inner arrays are basically the columns, no, the rows, sorry. But hold on a second. Yes, yeah, exactly. All right, so as you can see, you can actually infer the dimensions and stuff, but anyways, so now what's next? Now let's say we want to actually, for example, print line M, the matrix, right? Let's actually derive debug so we could print it, right? And let's try this out. Now, since this is a test, it won't really work out. Let me show you. Cargo B, yeah, or actually cargo T for test, cargo test. And there you go, but it doesn't print anything because by default, Rust test doesn't print anything. They capture the output. So what you could do is dash 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 no capture. And now you could actually see the printing stuff. As you can see, our matrix is printed here. Now let's say we want to actually index the matrix using, you know, row and column index, right? How we could do this? As you can see right now, we cannot do it just yet. But to be able to do that, there's a lot of ways you could implement the index. For example, but that's a lot of work. It's like you're gonna implement a lot of stuff there. Like you could implement the index, the iterator, blah blah, slice, whatever, which is a lot of work. Instead of that, we're just gonna implement deref. So let's see, we're gonna copy this declaration right here, and we're gonna implement deref for matrix, scalar, rows, columns. Type target is of course the 2D array, and let's actually yeah, let's import this guy. There you go. In fact, just for the sake of simplicity, I'm gonna import all the operations for now. All right, so next up we also need deref mute, and we need deref mute so we could do something like this, for example, you know, whatever. So you could change an individual element in the matrix. To be able to do this, of course, the matrix should be mutable. And secondly, you need to implement deref mute or index mute, I think. But anyways, let's see here what we got. Yeah, sure, that's good, great. And that's it for deref mute. Now we could actually do both of these operations, and we could also even take the iterator of the matrix. I have already covered all of this stuff in my previous stream about generics, so go check that out if you didn't yet. But yeah, let's just go forward with this. The other things that you could implement other than that is the asref, for example. Now this one I didn't cover in the last stream, but it's also interesting. So impl asref, there you go, as reference to the array, and it's kind of similar to deref and ref. Deref and deref mute. Basically what's happening here, like why we need this, is that let's say you have some function that takes as a parameter a 2D array, you know. So what you could do, instead of having to get the matrix and convert it into a 2D array, you could just pass the matrix directly. So like you could have some function, let's say f, you know, that takes asref let's say 2D array, or array 2D, or array, yeah, fine. And basically, let's say it takes as ref, and it takes let's just say too simply t, or let's just say i32, I guess. And then actually, let's do this and this, you know, something like that, basically. So instead of having to get, like, to convert the matrix into a array first, you could just pass either a 2D array, a regular one, or you could give it a matrix, because we have actually you know, implemented as ref. Is the stream still fine though? Okay, seems good to me. All right, so let's go to the next one. The other one that you could find useful is borrow. By the way, as ref also have as mute. This is, it's basically as ref but for mute, for mutable access, just like dref with dref mute. So it's same thing as mute, just like that. Pretty simple. So these basically are the traits you usually implement for types that just wrap other stuff, you know. Like, for example, here our matrix is just a wrapper over a 2D array. And other than as ref and as mute and all that stuff, there's also borrow. Okay. And borrow, basically it's like string and string, like string and str, you know, just like string, I think implements borrow. Yeah, it implements it for str or something like that. I don't really honestly understand this fully. Either way, these are the traits that you should have, like that you usually want to implement for your wrapper types. Now, instead of going through all of this craziness every time, we don't need all of this. You know, all of this, we don't need it. You know what we could do? We could use a library. Cargo add shrink wrap rs. It's a pretty useful library for wrapper types. Especially to what is it called again? Like when you have a problem with the orphan rule of Rust, you could use this library to make it much easier. So let me show you here. If we go to shrink wrap rs, there you go. So making wrapper types allows us to give more compile time guarantees about our code being correct. This is one of the applications. Now we can't mix up with and hide. The compiler will yell at us, but they're kind of a pain to work with. If you ever need to get that wrapped U64, you need to constantly pattern match back and forth to wrap and then wrap the values. Shrink wrap rs aims to alleviate the pain by allowing you to derive implementation virus conversion traits by deriving shrink wrap. So as you can notice here, that shrink wrap basically implements all of this stuff. It implements as ref, borrow, and dref. These are the things that we have implemented ourselves manually before. And you could also add this shrink wrap mutable to give also mutable access, you know. So the mutable counterparts to these ones, right? And there's also this shrink wrap transformers, though I haven't used this yet. I don't know how that exactly works. Either way. And there's also the shrink wrap main field and stuff. If you have multiple fields, in our case, that doesn't really apply to us. Anyways, so after you import that thing, you just need to derive shrink wrap. So derive shrink wrap, and of course you need to import it, I believe. Come on. Yeah, you need to import it. So use shrink wrap rs shrink wrap. And there you go. Okay, so we also want mutable access, so we can mutate the 2D array through the matrix. So we could also copy this guy. So shrink wrap mutable. And there you go. Now all of these methods that we have done manually before, it becomes very easy to do so. Just derive shrink wrap mutable. So the macro will do the job for us. All right, so that's the first. As you can see, it's still working just as expected. Great. Now what's next? Now we could actually go to the real deal. Okay, so let's see where to start. Let's go to Wikipedia. Alright, definition, size. We could start by size, for example. Like, let's implement, let's declare this guy matrix scalar. No. Let's implement size. Oops, self usize. Hello, Theo Paris. How is it going? Welcome to the live stream. So as you can see, we have implemented the size here, which basically just returns a tuple, or in this case, a pair of values, usize and usize, which are going to be basically the rows and the columns. Just like the definition here, though in mathematics, we start the indices of a matrix from 1, but here, since we're using a 2D matrix, like a 2D array, and in programming, we start with 0. You could change that by implementing the index yourself, like the index trait, but there's no need, honestly. It just adds overhead for no reason. So I'm just going to keep it like this. Okay, and that's basically it for that. What's next? Okay, so there's also these definitions. This is a row vector, which is a matrix of 1 so 1 rows, yeah, 1 rows and n columns. This is a row vector. A column vector is n columns and 1 row. Hold on, what I'm saying, yeah, exactly. And then a square matrix is n times n. So basically the rows and columns are equal. So we could actually easily do this, and you can notice here that if we implement the matrix, we could easily get a vector out of it. So let's see how we could implement these in Rust. Let's just define some types. Basically, it's just going to be like aliases essentially. So type row vector, and there you go. Scalar, const columns, usize equal to matrix scalar, one row, right? Because it's a row vector, and the columns that we got out of this guy. Cool. Next thing is the column vector. There you go. Same thing. And then finally the square matrix. And there you go. Now this have one value here. Let's call it dimension, I guess. Okay. So the dimension would be in both the rows and the columns. These are basically just makes it easier to deal with, you know. So like instead of saying matrix, scalar, dimension, you just say square matrix and then you give one dimension. Anyways, so that's basically it. You could also define some convenient types, like let's call it a vector exactly. Though you could just, so usually a vector is a column vector, I think. Yeah, usually. So we could just do that. We don't need this. And there you go. So you could just have some default values like this. But whichever. Alright, so that's basically how you do that one. What's next? The notation. As you can see in mathematics, they start the indices from 1. But since we're in programming, we just start by 0. Okay, what's next? Basic operation. By the way, I suck at linear algebra. It's like, as a programmer, I usually just use a library like NAlgebra. Most of the time, there's no need to actually understand like how the calculations are done and stuff. Most of the time. So we usually just, use a library that does that stuff for us. What is important for us as a programmer is just basically to know where to use those tools. So it's just like other libraries, like functions are like black boxes. What you need to know is just like, let's say, what happens, like what it means, like actually what matrices are useful for. For example, you could use matrices to transform spaces, like to transform from global space to local space, from one coordinate system to another, etc. You know how to use them as a tool. You don't really need to know how they're implemented. But anyways, though, it's very useful to know how they're implemented, like how to calculate that stuff manually, especially in, for example, in optimization. Though you could probably get away also with just tools like, I don't remember the name of the tool, but it's Simba or something like that. I don't know. It's in Python. But yeah, whatever. Anyways, so here we got the addition. So the first thing is the addition. The addition in matrices is pretty simple, just component-wise addition. So let's go ahead and implement addition. Okay, so impl scalar matrix. No, let's implement. Actually, let's just call this add, and let's see. There you go. Okay, let's see if the AI have done it. All right, so input scalar columns, rows, columns, add matrix, rows, columns, where scalar, add output equals scalar plus copy. If you don't understand what the heck I'm saying here, please watch my previous video. I've gone through this in very, like, a lot of detail. So yeah, type output equals self, fn add. Okay, great. Here it's saying, yeah, you could go this way, I guess. So result self. Yeah, that's row g element. Yeah, that's kind of fine, but honestly I'd rather do it in another way, which is to use std. Now this is fine as long as you have copy here, right? Because here we're actually, I think, copying the matrix. Yeah, since scalar is copy, that means the array would be copy. So you can hear like it's basically copying the whole matrix, but that could not be always an option. Like for example, big int, which allocates a vector in the heap, it's pretty expensive to allocate memory, so it's not copy, it's just clone, right? So if you have clone here, this wouldn't really work. You cannot do this. Hold on. Well, that's kind of weird. Either way, let's just go back, and I have a better idea of doing this. Std array from fn. Okay, now this gives us the index of the array. In our case, it would be the row. Yeah, the row index. This would be the row index. Right. Hold on, what's happening here? And here, say a std array from fn column index. There you go. Okay, so what's happening here? Yeah, we need to wrap this into self. Oopsies, there you go. Okay, so here we're just creating a 2D array using from fn, because doing it this way wouldn't work. Let's say doing it this way. Like this, rows, columns, 0, for example, because it's not necessarily 0. This is like int, but here we're working with generics. So what you could do, either you could go with scalar 0, but you gotta implement that trait, like you gotta constrain the scalar type to be zeroable, or otherwise what you usually do actually is go with default, in fact, default. So because in Rust you cannot have an initialized arrays. You can though within safe code, but there's no need since we have some interesting functions like from fn here. But yeah, either way, just go to my previous stream if you haven't already. I really explained this a lot. Anyways, so for now let's just go with this. Okay, so here we're creating a 2D array, and so for every entry we're calling this, you know. So here we get the row index and here the column index. So what we're saying here is self row index, index column index plus RHS, which is the right hand side, row index, column index. So basically this is just component wise addition, right? So that's basically it for add. Okay, what's next? Scalar multiplication. Scalar multiplication. So how we could do that? Well, let's see. Let's see if the AI would do anything good here. So right, row columns where copy. Oh, by the way, we don't really need copy. Because if you don't, like if you use copy instead of clone, for example, you will lose your, like, it would be less generic since you cannot use it with types that aren't copy. So, but a lot of types are clones. So, because basically copy is like a subset of clone. But anyways, error cannot move out of type, and non-copy array cannot move out of here. It's basically telling us that you cannot move the value out, so we have to clone it. And instead of copy, we could constrain the type by clone. And here what changes is just instead of copying implicitly, we copy explicitly using clone. Here, same exact thing, we're gonna clone here too. Though this is not the best performance wise for but well, this works. Alright, so that's basically it. Great, so that's add. Next up we have is scalar multiplication. Now notice one thing though, notice here one difference is that here in addition between a matrix and a matrix, we just say add, you know, we don't say add scalar like here, right? Because this add trait have a generic parameter called RHS, which is the right hand side, the type of the right hand side of the addition, which is by default is equal to self. So if you don't include the parameter here, it's basically self implicitly, right? But we don't need that. All right, here we don't want to multiply a matrix by a matrix. Here we actually want to multiply a matrix by a scalar. That's why we add scalar here as the right hand side type, RHS. Great. So here in mul self output, yeah, there you go. The AI have picked up on my code right here. There you go. That's good. It's basically kind of like component wise multiplication. But here, instead of having a matrix, you have one value, one scalar that you multiply with. All right, next up. Okay, the beast, the matrix multiplication. But before that, let's go to the next one, subtraction. Okay, so subtraction, you basically say b times -1, right, plus a. We have already implemented the addition of the matrices. We have already implemented the scalar multiplication. So now we can implement subtraction. Great. So let's see how we can do that. Ooh, okay, what I've done. All right. So let's go with matrix subtraction. Okay, let's see if the AI did it correctly. All right, so matrix subclone. Oh, by the way, here this is copy. No, let's make it clone. Okay, I think we just gotta say clone here. Oh, maybe here. Hold on. What? Error cannot move out of type. Yeah, makes sense. Makes sense. I see. So let's clone this, I believe, too. And there you go. So that's how you use clone instead. Great. Now for the matrix subtraction, what we got? Sub for matrix. Great. Type output sub from fn row index column index. By the way, in mathematics they usually call it IG, so instead of row index they call it I, and instead of column index we call it G. But in programming we prefer some good names right there. Anyways, self row index column index clone minus, so basically component wise subtraction. Though to be honest with you, you can see that we have repeated some code here. So like a CD array from fn, a CD array from fn, blah blah. So we could indeed abstract that, I think. The issue is what we should call it. That's the hardest problem in programming, what you should call it. All right, anyways, let's see. So we're gonna implement some method here that could make it easy for us. Matrix scalar, and here instead of iter we're actually gonna go with, I guess let's call it apply. No, let's actually call it maybe combine component wise, I guess. I don't know, but something like that maybe. Self, and then you're gonna get RHS, which is also gonna be self. Here though we're gonna go with self combine component wise, and we're gonna have some closure. And this closure could be just impl fn ones fn, no fn, it's gonna be fn, I believe. So fn, if I'm not mistaken, it's like this. Arced tuple. Oh, no, not like this, right? And here the output would be scalar basically, and the input would be yeah, it would be scalar. Okay, so it's basically a binary function, right? Like, hold on, is it, should it really, binary operator, sorry, yeah. So it takes two parameters and it gives us back one parameter, right? Cool. So now what this returns is, well, self, right? Great. Now we could just copy this, put it here, and instead of this we could say, we could remove this plus, and instead of plus we're just going to call this function. Right? That's pretty much it. So yeah, self row index column index, RHS row index, and that's pretty much it. Now we could use, instead of this craziness, we could say self dot combine component wise RHS, with the f being scalar add. Look at that. That's basically it. Now we could do the same thing with, I really love such abstractions. Anyways, so scalar multiply. Ooh, what I'm doing. Well, this is actually quite interesting, because this is gonna be, instead of component wise, it's gonna be like scalar component scalar wise. I don't know what to call it, honestly. We could call it actually scale, right? We could call it scale, I believe. But is there any need though? We only have one method that does that, I guess. Yeah, I don't think there is a need. Though it may be interesting to abstract this from fn into its own function. And yeah, from fn. So like we could have some function f, let's say, right? And this function f gives us back self, and you basically give it self and some f. And this f would basically take usize, which is going to be the row, like the column index or whatever, or the row index, then the column index here. So usize, and it gives us back a scalar. Great. So now it would basically be like this, but without this guy. It would be just a row index and column index here. Sweet rain. Let's go. What should I call this? Is this, oh yeah, this is actually very similar to something I've read in here somewhere. I forgot where exactly. Hold on a second. I'm pretty sure I've read that somewhere here. It's like basically generate by formula. There you go. Sometimes the entries of a matrix can be defined by a formula, such as aij equal fij. There you go. That's what I'm talking about. That's interesting. So can be defined each of the entries of the following matrix determined by a formula. We could actually call this new, maybe. New. I'm not sure. Or we could call it from fn. Or generate. Whatever. Anyways, I guess let's call it generate maybe. And here instead of this, we could let's just copy these, I guess. And here instead of this craziness, we could just say self.generate. There you go. Okay, what's going on here? Oh, I see. So generates actually takes self, which consumes it. That's interesting. I guess we could just take a reference to self here. Yeah, it's fine. So self.generate row index, column index, then f, which is our function here. Self row index, column index, clone. Do we really need clone here right away? I do think so, yeah. All right. Okay, so there you go. So we have created generate function and the combine component wise. Yeah. If you guys have any better name, let me know. Anyways, so that's pretty much it. Now this is for add and for this one here we could say generate, and let's just grab this guy and let's just say exactly, yeah, self.generate row index column index self row index column index dot clone times RHS dot clone. Great, that's multiply. Next up is sub. There you go, as simple as that. Combine component wise scalar sub. That's pretty cool. Let's go. That's the matrix subtraction, pretty simple. Though you can notice here that we didn't do it like the mathematical way, which they have built upon the previous ones, right? The previous, like here basically they first defined addition, then they defined scalar multiplication, then in subtraction they have like built upon scalar multiplication here to turn b into its, what should we call it, into its negative side, I guess. But anyways, but in our case we just said a minus b directly, though if we want to match exactly how the mathematical way here is defined, we could say instead, let's see, let's just comment this out for a second, and we could say add, isn't it, right? Yeah, we're gonna need add, and we're gonna need multiplication by the scalar. Yeah. B. So do we even, yeah, what the addition needs, hold on, scalar multiplication needs this guy. But either way, let's actually start simple, very simple. Let's not do any of this for now until it yells at us. Okay, so error, no function associated, item name, sub what. So sub, yeah, great. Now here, combine component wise. Not really. We're gonna actually do this. So self.a. So first of all, we actually have to like multiply it by -1. So let's go ahead and say self times. But here we go. We have a little problem here. It's like scalar is actually a generic. So we don't know like what is -1 of it. We could implement like a trait that does that kind of like, it would be like a -1 or something, or otherwise we could actually get 1. Yeah, I see. So here's a little way of doing this, I guess. Cargo add num traits. It would be a little exercise here, a little fun exercise. Okay, so I added num traits that basically contains some traits that are common for numbers. You could just check out again my last stream. Anyways, so RHS dot okay, so we're actually gonna say scalar 1, right? But here of course we're gonna need to constrain scalar to have 1. Basically, there you go. Now what's happening here? Let's actually import that. Okay. Oh my god, something entered my eyes. Bruh. Anyways, use num traits 1. So we just get the 1. This is basically a trait. Right, so scalar should have the trait 1, and then we could say times scalar 1, but that would only gives us like self back, right? But we actually want -1, so we have to say minus scalar 1 here, right? So, and since we said minus, we also have to use neg output scalar, exactly. So you could get the negative, the unary minus, you know, operator kind of. Negate, right? The unary negation operator, right? So that's nice. So we could say this, and 1 for this, and so on. And that's how you do that one. Next step is we need, but here B, it should be B, yeah, my bad. So RHS, and here self plus RHS times that Cannot add matrix scalar rows to matrix scalar rows columns. Huh, why? What are you talking about? Well, that's weird. We have already defined addition. Yeah, I think maybe we're missing something from addition. Hold on a second. So where's add? There you go. It needs to be addable. The scalars needs to be addable. So scalar here, we need it to be addable. So there you go. Okay, right now it should work out just fine. Let's at least see if it builds. Yeah, it builds, so that's good enough. And there you go. That's how you do it the mathematical, like the way that they have done it here, right? So that's pretty cool. But notice it's not the best programmatically, because right now you're constraining the scalar type to be negative and, you know, all this crazy stuff, like to be negated, right? And all that crazy stuff. And also it's not the most efficient. But anyways, so let's just remove this for now, and let's just go with this for now. Matrix abstraction. All right, great. Now what? We don't need for now. Well, actually, we're gonna need it later. Yeah, since now we actually have defined addition, we could also implement the identity, the additive identity, which is basically 0, right? So how we can implement it? Well, in fact, we have already added num traits, which gives us that. So let's go ahead and implement it. So additive identity. There you go. Let's see. Cannot find trait. We gotta actually import it. Use num traits 0. There you go. So scalar should be zeroable first of all, because if scalar isn't zeroable, then how we can define the 0 of the matrix itself? Oopsies, what's happened there? I don't know. Anyways, so here, self array from fn scalar 0. Notice that this keeps on popping up. So instead of this, we could just say self.generate scalar 0. There you go. And here we don't need the indices. Okay, cool. But what's happening? Oh yeah. Oh, I see now. Because we don't have self. Though we have, well, yeah, this is a member method, not. Makes sense. So we need a freestanding method for that, because this doesn't take self. It's a static function, not a method. So std array from fn. Well, we could make a freestanding function for that if we really want to. And I don't know what to call it. Let's see. It's basically gonna be a 2D array of some type T, let's say, and there you go. And here we're just gonna go with F, right? F. Here we're gonna need the row index, and here the column index. Great. And so we need the row index here. So this is a freestanding function. Great. Hold on a second. Are we even using self here? Yeah, we're not. So it's useless, isn't it? Yeah, we're not using it. That's cool. Alright, so yeah, we don't really need to make it a standalone function. Like, I mean, we don't need self. in the first place. Ooh, well, that's interesting. I didn't notice. So no method name generate found. So we could just say self generate right now. And actually that makes sense because this is basically a constructor, right? It's like new. So yeah, that makes whole sense. I don't know how I didn't notice that. Anyways. So what's happening right now? Okay, so that's good. X is 0. No method named is 0 found for. We're gonna come to that later. So self generate. Here though, we're gonna need self because we're using it. Anyways, there you go. Self generate. Here X is 0. So that's good, okay, but what's going on here? Yeah, I see, because this is a reference. So we could say clone, like we could say the cloned, I guess. No method named is 0 found for an array. Huh. Oh my bad. We have a 2-dimensional array here. So let's say, so this is going to be basically the row, right? So we have the row. Now we also need row iter all is 0, okay? So basically we iterate through the rows, and then through every row we iterate through the scalars in that row, and we check if all of them are equal to 0. If all of them are 0, then of course our matrix is 0. And that's the additive identity. Let's go. Pretty simple stuff. For the matrix, like the multiplicative identity, we cannot do it just yet until we until we defined the multiplication in the first place. Because without multiplication, you cannot have an additive, like a multiplicative identity, right? So multiplication would be a beast, especially with generics. We're gonna see about that. Cargo B. So what's next? Let's see. So we have implemented addition, scalar multiplication, subtraction, and now transposition. Okay, so transposition is pretty simple too. It's just like the columns becomes the rows and the rows becomes the columns, right? So as you can see, 1, 2, 3, it becomes 1, 2, 3 like this. 0 minus 6, 7, 0 minus 6, 7. Okay. So let's implement the transpose. So basically what happens is that some entry that is inside of IG becomes AGI. So instead of IG, it becomes GI, right? Those are the coordinates basically. Alright, so let's go ahead and maybe try to implement that, I guess. And by the way, this needs clone. But here, this generate function, we don't really need clone. This clone, we only need it for this guy. So we could actually put this in another impl block where it is not constrained by clone. Just to keep it as generic as possible. Because here we're just adding like a fake kind of constraint for that function. Right? So that's why we need to split, for example, these two functions, because generate here doesn't really need this clone bound. Like the scalars doesn't need to be cloned to be able to do this, right? That's why I put it in a separate impl block. There you go. Great. What else? So let's actually implement transpose. Now for transpose, well, in some sense, we're basically swapping, right? Or isn't it? Yeah, I think we're swapping. We're swapping one element. Like here, for example. Does that even make any sense? But we'll see. We'll see. Let's just implement it and find out. Of course, there's a lot of ways to implement all of this, but yeah, we're just going with showing you hopefully some ways to do stuff. Anyways, so let's try transpose here. I'm not sure if we're gonna need clone just yet. Probably we're gonna need that, but we'll see. So matrix generate. Here we get the row index and the column index. And here we say self column index. What? That's actually interesting. Hold on, what? I mean, yeah, I kind of understand, but it's actually quite... Hold on. So it generates row index, column index. Yeah, here because we're basically generating a new matrix, right? Yeah, that's why it works. Yeah, I was actually thinking about swapping the thing because I thought like I'm gonna do it mutably in place, which is not the case here. We're just generating a new matrix, right? But instead of row index, we just go with the column index. Like we just, yeah, basically just like the mathematical definition here. Though, yeah, there is another way that I was thinking about, not this way, I guess. So the other way that I was thinking about, let me see if I could actually do it here. It's gonna be very similar, right? Actually, we don't need matrix, blah blah, self here, and the same thing here actually, self, great. That's basically it. All right, so let's see what we could do here. So this gonna give us self, and this actually means, do we really? Hold on a second. Do we really need clone though? I don't think we do. Because here we're actually taking self by value, right? We're not taking it by reference. But do we want to take it by value or by reference? Well, depends on your use case, right? But I guess for now we could keep it like that. Fine, whatever. But let's just say this now, and let's say, so basically what I was thinking about is that we could generate some matrix, right, with default values. Then, but yeah, you're gonna create another, like you're gonna need the default constraint, like you need to constrain to default, which is not great. While transpose here doesn't even need clone. That's pretty cool. Anyways, whatever, let's just go with this one. That's pretty interesting. Let's put it here with generate, which doesn't have any bounds. Or is it? Cannot move out of type. Why? Okay, but why didn't actually tell us? Yeah, and I understand why that's the case, but like why it didn't tell us here? It does tell us, but yeah, it was too late. I see. Yeah, it confused me right there. Anyways, I guess I'll just go with clone here. So we do need clone, yeah. Though it does make sense to swap it out, because we're not gonna need that anymore. Anyways, whatever, this is fine. That's transpose, and this is generate. Great. Let's go to the next one. That's transposition right there, pretty simple. Matrix multiplication. There is, by the way, one interesting property that I've seen before. I don't remember where exactly. Hold on. Did I miss it or something? Maybe it's still... It's called mirroring, I think, or something like that. I don't know. Weird. There's no... It's actually symmetric. Yeah, my bad. Symmetric. There you go. So a square matrix A that is equal to its transpose, that is A equal A transpose, is a symmetric matrix. And that makes sense, because if like basically what transpose does is like one part of the matrix, right? It's just like swaps it with the other part, right? Symmetrically, kind of. So basically the value that goes here will become here, and the value that was here would become here, and so on. But if you have, like, let's say this element is equal to this element, even if you've swapped them out, you still have the same element, like the same matrix, right? As long as all of them are like that, right? For the diagonal, like the elements in the entries in the diagonal doesn't really matter, because when you transpose, like the elements or the entries in the diagonal of the matrix doesn't really get, what is it called? Yeah, it doesn't get touched, you know, it doesn't change, right? They're just gonna stay there. It's like it's in the line of the symmetry, right? So anyways, symmetric or skew, and of course this only makes sense in square matrices, not any matrix. And if you think about it, it makes sense, because, well, in a square matrix it's very obvious what is the line of symmetry, right? Which is like what is the diagonal. But in a matrix that is not squarish, like how would you define that? The same thing as the multiplicative identity, as we're going to see in a second. It's only defined for square matrices. So anyways, whatever, that's pretty interesting stuff. Symmetric, skew. But yeah, we could check this out. We could check for this. What is it called? Hold on. Symmetry. Symmetric. A square matrix A that is equal to its transpose, that is A equal AT, the symmetric matrix. Hold on a second. If instead A is equal to the negative of its transpose, that is A equal minus A transpose, then A is a skew symmetric matrix? What is this? I only have read this, so there you go, symmetric matrix. Alright, but what is skew symmetric? I mean, I kind of understand, but I don't understand at the same time. Yeah, it's basically the same thing, but it's the inverse, right? Okay. Symmetry is often replaced by the concept of Hermitian matrices. Well, that's beyond me. I don't know what's that stuff. Which satisfy, I don't know what that means, where the star of asterisk denotes the conjugate transpose of the matrix. That is the transpose of the complex conjugate. What? This is beyond me. I don't know. Hold on. Oh, it's actually about complex matrices, I guess. I don't know. Anyways, whatever. Whatever. By the spectral theorem, real symmetric matrices complex. Alright, anyways. So there, that's beyond me. Still don't know that stuff. Alright, so let's just, for example, implement this symmetry functions. So how we could implement those? Well, remember that we need it to be a square matrix, right? So we could use our square matrix alias here. So we're gonna implement scalar, comma, instead of rows and columns, we're only gonna implement one dimension, right? We don't need two. And there you go, square matrix. Not identity. Const dimension usize. And here we're gonna check for symmetry. Let's see. Okay, is symmetric. We're taking self and we're given a bool. Basically, it's a predicate kind of. Self iter enumerate. Why do you need enumerate? Enumerate all row index row up to row index iter all. I don't get it what it's doing there, so I'm just gonna disable the AI for now. I'm just trying on my own. Disable completions for a second. And let's see how would let's just do it the normal way, like the mathematical way, although it's not the most optimized, but let's just do it. I think we basically need self is equal to self.transpose, as simple as that, right? But of course we need the binary operator equal, so we need to implement equality for our matrix first of all. So let's actually enable Copilot here. Let's go. And let's see if Copilot, it should be pretty straightforward, just like add, it's gonna use combine component wise. So let's see if he could do that. Partial EQ. So const rows coms partial EQ for matrix. Partial EQ is like is the, hold on, what is the name? Like I forgot what is the name. Anyways, where scalar should be partial EQ, of course. Bruh. Anyways, fneq boolean self iter zip. So we zip with the auto iterator. Great. All row auto row. Nice. Or let's call it, instead of auto row, let's call it RHS row, right hand side row, because order matters. Just to make it very obvious, row iter zip row RHS row iter all, and all of them should be equal. Yeah, that's great. That's great. Nice. We could instead, for example, self iter zip auto iter, and then maybe we could flatten it or something and just but anyways, this is fine. So that's the equality. Now I could actually hopefully do this. Why? Self and self transpose. Yeah, because this needs to be a reference. At least that's what we're defined it here for, I guess. Cannot be applied to type. Yeah, my bad. My bad. The scalar should be partial EQ. So let's actually do that. Plus partial EQ. Okay. Can't compare. Let's actually get the transposed. Because this gives us an owned matrix, right? And here I think we have implemented equality for reference, as you can see here, not for owned matrices. Cannot move out of self, which is behind shared reference. Oh yeah, because, yeah, I see what's happening there. We gotta actually clone this. Otherwise, transpose would actually consume it in our case. But does it really need to consume it? I don't think it does. Yeah, no, it doesn't need to consume it. So that's great. So we don't need clone there. Nice. So that's good. So we just transpose self, and then we check if it's equal. That's as simple as that. That's pretty cool. Otherwise, other self. Yeah, this is good. Good enough. Okay, fine. About other than that, there's also check if skew symmetric. Great. Let's go ahead and do that. It's pretty simple, just minus transposed. But I don't think we have implemented nig yet, which is negate. Yeah, we didn't. Makes sense. Though we could maybe say matrix 0 minus transposed, because we have implemented sub and we have implemented the 0, I think. So we could indeed say, so minus transposed. Oh, well, yeah. Let's say matrix. Hold on, what I'm saying, self 0, right? 0 minus. We could say this, but of course 0 needs some stuff. 0, where is it? There you go. It needs scalar to be 0. And also clone. Clone, we already have that. So cannot subtract matrix scalar dimension from matrix scalar dimension. What are you talking about? Why? Why we cannot do that? And we don't need that. And let's just call this result, I guess, whichever. Or like actually the negative transpose, I guess. Maybe it have a more technical word. I don't know about that. Cannot subtract matrix. Let's see our sub implementation. Where's sub? Sub. Bruh. There you go, okay. So it takes self and also takes RHS as self. Then gives us back self combined components twice. Or actually, otherwise we could just say, no, we haven't done that. What is the problem? Hold on, let me see the whole error. Okay, yeah, scalar needs to be subbable. My bad. There you go. So we need that too for subtraction. But I think output should also be equal to scalar, I believe, isn't it? There you go. Okay, so right now this works. But what's happening here? And there you go. So that's skew symmetric. We just took a 0 matrix, you know, minus the transpose of that. Otherwise, we could implement nig for the matrix. We could implement nig here. So we need this, for example. And let's implement nig for matrix. And scalar needs to be negatable, if that makes any sense. Minus x cannot apply to type. Yeah, this is the row. I don't know why the AI always gets this wrong. Anyways, so row dot. Well, we actually want to generate a new thing though. Hold on. What it's doing. Self generate. Okay, there you go. And you don't need this nig. Just do we even need clone? I think, yeah, we do. So, and we're just gonna say minus here. Yeah, that's simple as that. That's negate. Otherwise, we could just say directly this. Oh, what I'm saying. Yeah, we could say this, right? Instead of this, we could just say minus self, right? Simple as that. The function associated item 0 exists. But we need these all this stuff right here. So no, let's just keep it simple. Like this, right? Okay. So now we got the negate. Now instead of this craziness, we could just say this directly. And hopefully, what is happening? Cannot apply unary operator to try. Yeah, because it needs neg. So instead of this craziness that we got here, which is 0, we don't need 0 anymore. We don't need sub anymore. Now we just need nig and clone. Clone, we already have that, so we just need negate for scalar. So as you can see, it depends on which constraints you want to choose and what's your priorities. Is it performance or what exactly? But yeah, for me as a tutorial, just do whichever like is convenient basically. Anyways, minus self dot transpose self negative equal to that. Okay, great. That's one thing. So what's next? By the way, does this compile just fine? I think it does. Just to make sure. I'm not very concerned about tests, but if this is an actual library, then you probably want to do some extensive tests to check for every function if it's doing the thing that you're expecting it to do. But like, I don't think I've made a mistake, so I mean, it's simple stuff. But it's always worth it to actually always make tests. Wa alaikum salam, G Gearing. Welcome to the live stream. How is it going? And there you go. We have checked, like we have made some functions to check if a square matrix is symmetric or skew symmetric. And since we have only implemented it for a square matrix, it only applies to a square matrix. Where is square matrix? There you go. Okay, so as you can see, instead of a matrix, we have actually applied it to a square matrix there, and we only needed one generic constant, right? Like one constant instead of two. Anyways, whatever. And that's actually great because transpose, I think, no, never mind. Anyways, so that's pretty much it for those ones. Next up, let's go back. Yeah, so right now we got the matrix multiplication. Okay, this is gonna be crazy. I always find this very confusing. Anyways, so basically matrix multiplication, what you do is that for every entry you just take the dot product of the row of the first value, like for the first, like LHS, the left hand side, and then like with the column of the right hand side. So basically dot product of the left hand side row and the column of the right hand side. Anyways, so let's see. So basically multiplication to matrices is defined if and only if the number of columns to the left. Okay, so this is actually, first of all, we have a condition, is that is defined if and only if the number of columns of the left matrix is the same as the number of rows of the right matrix. So if A is an M by N matrix and B is an N by P matrix, then their matrix product AB is the M by P matrix, whose entries are given by dot product of the corresponding row of A and the corresponding column of B. Okay. basically what this means is that, let's say A is an m by n matrix, right, and B is an n by p matrix. Basically, notice here that the columns of the left hand side should be equal to the, like, the dimension of that is equal to the dimension of the rows of the right hand side matrix. Yeah, basically. So instead of having we would had basically m and some other generic, like some other constants here, and p. But since these, like, it's only defined for if the number of columns of the left matrix is the same as the number of rows of the right matrix, we only need 3 constants: m, n, and p. So let's see how we could do this in Rust. But before that, actually, we need another operator. First of all, we need to be able to get columns. Now, I think our implementation is row major, which means that, like, the rows are in one array, right? But now if you want the columns, that means that we have to construct it from scratch, right? So we need, first of all, a method that could get the column. We don't really need a method to get the row though, because it's as pretty simple as just, indexing into the matrix. So let's actually implement that. Let's see. So fn, we actually do need the clone, right? So let's go ahead and say fn column. Column, and it's saying column vector. Column index expected function tuple struct, or expected function tuple struct, or tuple variant. What are you talking about? Oh, can't use a type alias as a constructor. Why? That's stupid. Why you can't? Well, anyways, we could just say this. Or actually, yeah, basically, could say this instead. What? What's wrong here? Scalar rows 1. Mismatch types label expected scalar 1 rows found scalar. Ooh. Oh. The AI is stupid, I guess. Hold on a second. Well, instead of doing this stupid stuff, I guess just say column vector. Oh, I see. So it's thinking that column vector is one dimensional. Well, it is kind of. Anyways, let's see. Let's just do it ourselves. Column vector. And I guess we could maybe use generate here too. Yeah, we could use generate. And we're gonna get the row index, correct? The column index, we don't care about it because it's always gonna be constant in this case since it's a column vector, right? But we already have the column index, so we don't need this guy. Hold on a second. Column index. kind of confused actually. I don't know. Anyways, for now, this is find row index, self row index, column index. As you can see, column index is actually constant because here we're getting the column vector, right? The row index changes depending on the row, basically. And we clone there. So that's basically how you get a column vector. Great. As you can see, we're just generating a new array and make keying a column vector. I got device loss after I called dispatch 555x55. Device loss in Vulkan is basically happens when you have made something wrong that isn't like that doesn't confirm to the spec or something. But basically it's kind of like usually for undefined behavior, or it could just happen for whichever reason, you know. But in this case, since it happened for dispatch 555, then maybe you're doing something wrong. I'm not sure about the whole spec of Vulkan. Anyways, column vector generate. Great. So this is how you take a column. Next up is we need to be able to take an array and get the dot products of that array with another array, right? If that makes any sense. So how are we gonna do this? The easiest way is to just make a freestanding function like this. Fn dot product. Ooh. So here just taking an iterator. Maybe. Basically, iterator is more generic than array or a slice. So let's see. Yeah, I guess fine. We could easily turn an array into. We'll see. We'll see. Scalar. Okay. So here we're implement like impl iterator item equal impl iterator item equals scalar. What? No. No. Just one dimensional in our case. So regenerate this mess. We basically zip LHS with RHS, and then we map XY. We clone X. Let's just see without cloning. X times Y, basically. We multiply component wise. This is essentially what it is. Zip and map. Then we fold. We use fold to basically sum up everything. So we start with a 0, and then we keep on accumulating, you know, accumulator plus X, and it keeps on going like that until we have summed the whole thing. We cannot use reduce unless if you want to return option here. So yeah, we could also use sum here, but sum is kind of weird because they have its own kind of constraint. I've never used it, honestly. But anyways, so what we need here, of course here we need impl block, or like impl, right? And then scalar 0. Scalar should be zeroable if you want this. 0. Because otherwise, if you don't want to use fold, as I said, you can use reduce, but then you have, instead of returning the scalar, you have to return an option. So, but anyways, so that's basically it. And here, instead of this, we could just say scalar add, really. And there you go. That's a dot product of two iterators, which is more generic than arrays. So here's how we can use it now. Let's see where we were. Yeah, we haven't done it yet. Yeah, so this is the beast, right? Matrix multiplication. Okay, let's see what the AI would do. Scalar rows columns multiply for matrix scalar rows columns. Scalar 0. It's already wrong since they only have 2 generics, which we actually need 3 generics because we have 2 matrices of not necessarily the same type. Though here it is assuming that they're the same type. So it's not really generic, you know. Because it only implements for the same type, basically. Which is not the whole story. Right, but anyways, let's see if it even does this correctly. Self-generate row index column index dot product. Great. Self row. Yeah, I didn't understand where to get the row. Basically just do this. Dot iter RHS column index iter. Great. So here we're just turning these into iterators and passing them to dot product. And this actually gives us back an iterator, I believe. Yeah? Or no? Let's see. Yeah, actually it gives us back a scalar. Right, my bad. What's happening here? Why it's actually doing that stupid thing. Anyways, so we're getting back a scalar, which is great. So what is the problem here now? Expected type parameter scalar found reference. Yeah, we should actually, instead of iter, we should say into iter to consume, because here we're getting the values by value, if that makes any sense. So into iter here too. What's going on? Column index. Expected. Oh yeah, I see, my bad. All right, let's see. Well, we know that we only gonna have one thing there, so we could just say 0, I believe. Yeah, or no? Yeah, I think so. And then we could say into iter here. What's happening? What column gives us? Yeah, column vector, right? Well, actually, column vector would be something like this, really. Yeah, it would be something like this, you know. Yeah, something like that. Right? This is an example of a column vector. So, no. My bad. Okay. But actually, this is not what I meant. Yeah, this is not what I meant. My bad. Yeah, I see now. This is not what I meant. What I really meant is just an array. To return an array of scalar rows, right? So regenerate this guy. SCD array from fn row index, self row index, column. Yeah, okay, that's what I want. Correct. Row index, column index. Column index is constant. Okay, great. So that's exactly what I want. Now this should work out into iter. Cannot move out of type. Why? Because it's a non-copy array. I see. So. Well, the nice thing though about vector, I think, is that it doesn't allocate on default, doesn't it? And we can actually move out the value and leave default in there. So like, hold on a second, Rust vec default. So it implements default, which is basically creates an empty vec. The vector, there you go, will not allocate until elements are pushed into it. That's interesting. So we could use this as an optimization for types that uses a vector. We could basically move out the value, right, and leave in its place a default value. And in the case of a vector, it's not costly at all because it will not allocate, because an empty vec doesn't allocate until you start pushing at least one element, you know. So that's pretty cool. So we could do something interesting. Could use std_memtake instead of cloning the whole value, I guess. So but then we would need to take the whole well, if we want to do this, actually we need to construct a new array, which is actually fine. Yep, need to construct a new array. And honestly, that's overcomplicating things for now. Let's just say clone for now. Yeah, into iter. Yeah, that's fine for now. Later on, maybe we could make a separate stream to try to optimize this out. For now, this is fine, I guess. So what we're doing, we're generating a new matrix, right? Row index, column index, and we're doing the dot product. So basically that entry, that specific entry that we're currently in of row index, column index, it's basically equal to the dot product of the left hand side's row, hold on, what am I saying, column, what, hold on. So we're using row index, right? So here we're getting a row. Yeah, we're getting a row, right? So here we're getting a row and we're passing it to the dot product, and here we're taking a column of the right hand side. Is that the case? And so row, column, yeah, I think that's the case. So that's nice. The problem though with this implementation that the AI have done is that it doesn't apply for like matrices that are different. Like for example, this would work for matrices, let's say, that are in this shape, you know, like the shape 1, 2. So basically 1 row and 2 columns times 1 row and 2 columns, right? So basically, let's say it works for these kind of things, right? For x, y times x, y. But the thing is, ooh, hold on a second. Yeah, the problem though is that this should be the same as this. So it's not really constraining that. I don't know how that would work in practice. Either way, this is wrong, right? That's the first thing. And let's say this got fixed, right? Let's say this is equal, right? The other problem is that these, like in multiplication, these could be different. And in fact, yeah, it is different, which is nice. But basically, what should be done here instead is z here and z here, right? So these should be the exact same thing, right? For matrix multiplication to be valid. So let's do this. Rows, columns, and we're gonna need the columns of the right hand side. We don't need the rows of it though. So LHS or RHS, my bad. RHS columns, usize, right? So now that we got that third constant, Now what we could do, instead of self, we shouldn't do this. We should say matrix, scalar rows, RHS columns, right? So that's nice. Rows, RHS columns. Great. But what's happening? Why it's erroring? Ouch. Rows. We're using it here, so what's up? Expression using a Cosmos map which matches things output value. I'm confused. Am I missing something here? Oh, my bad. So here rows. Yeah, correct. But instead of columns, it's going to be RHS columns. Yeah, exactly. Just like that. But then, what are we going to do with the columns, though? Super confused now. No, my bad. Here there should be columns. Yeah, this is actually right. I'm not sure why it's erroring. So for a matrix that is of rows and columns, we have the right hand side of columns. This should actually work. Oh, I see what's wrong. Yeah, so mul by default, you know, it's the right hand side is self. So we're really not using this, right? We're not constrained by that. So we should actually change this to matrix. So this is the right hand side type. It's going to be a matrix of scalar, right? Now, the rows of this matrix should be the same as the columns of the left hand side. And of course, we have our right hand side columns, which is not constrained by the other matrix. Great. Now, instead of self here, we should actually do the same thing. About this. And what's happening now? My bad, it should be this guy. Right hand side type. And now, expected matrix scalar rows RHS columns because of return type. Expected RHS columns found the columns. Is this correct? So we're basically adding some matrix of scalar rows and columns. Okay. To a matrix of yeah, columns, and then RHS columns. Great. Now type output matrix scalar rows. So this is the result now. It's going to be the rows of the first matrix and the columns of the second matrix. That's why it's called the outer products, I think. Anyways, RHS columns. Yeah, that looks good to me. I'm not sure what I'm doing wrong here. So expected struct RHS columns, but it's for some reason it's getting columns. Yeah, it's probably telling me that I'm doing something stupid here. Yeah, I'm probably doing something stupid. Expected RHS columns, found columns. dot gives back a scalar. Generate just infers the type from output. But what is happening wrong? Is the dot product good? Let's see. Zip map fold. Use back a scalar. Yeah, it's really irrelevant, I think. It's irrelevant. Now here we're taking the column. The row. Yeah, the row. So basically this is LHS row, just to kind of calm this out a bit. Into iter and RHS column. This is what we were doing. So RHS column is scalar columns. Ooh, why it's not giving us RHS columns? What? That doesn't make sense. Yeah, a column is supposed to give us that. Oh, this guy gives us rows. What? Does that make sense? Yeah, rows and columns really confuses me. Let's see. So when you take a column, right? Column. So this is row, this is column, right? Now, column would have the size of rows. So that makes sense. So yeah, something is weird here. Let's just say to do here so it doesn't error out. Expected found to do, because it's very annoying. It just doesn't want to remove the error. Well. Let's disable completions for a second. Maybe let's redo it. RHS columns. Multiply matrix scalar. In fact, we could do something interesting maybe. Let's see. Multiply matrix. I don't know. Anyways, so multiply silly returns. Yeah, my brain at this point is done. Probably missing something very, very idiotic. generate. So generate, we're getting the row index and the column index of the entry that we're looking for, that we're generating currently. Okay, so let's just go closely with the finish. So what we need, so we are in one of these entries. For example, let's say this. What we should do is get the row so row index, right? Bruh, it's very confusing. And actually, let's say column, right? And let's say row here anyways, just to keep it very descriptive. And row is basically self index, simple as that. Let's see, so this is scalar columns, right? Yeah, pretty much. So that's nice. So rows, columns, great. So I don't think that's wrong at all. Now basically we need to take the row of the LHS. So row is equal to LHS dot self dot row index, right? And then the column would be RHS dot column index. And then we take the dot product of row into iterator and then column into iterator. And yeah, that really should be it. I really don't get it. No way. In fact, this is not even a problem with this guy. Let's say 0, for example, for now. Oh. Yeah, let's say, for example, scalar 0. Or, yeah. That's not the problem. The problem is in... hold on, what? Now, the resultant matrix, right, the output is like half the rows of A, of self, right? So rows, and it have the columns of B. We're doing exactly that, RHS columns. I really don't understand what's going on with this. And the columns of the first. I really don't get it. Like, what? I actually did this before and it was fine. Probably should get a break at this point. Rows, columns. So we have 3 generics, which is fine. So 3 constants basically. So that's good. Multiply, and this is the RHS. Matrix, scalar, columns. Is it a problem with generate? Is it a problem with generate? Okay. Maybe it's a problem with generate. Hold on. I think, yeah, maybe generate is not generic enough for this. I guess so. Bro, if that's the case, that's crazy. I'm very confused. Oh. Now I understand. Instead of self, we need output. Bruh, like, really? This is ridiculous. I told you it was gonna be a stupid thing that I forgot. How long have you been coding in Rust? I honestly don't know. But can I see somehow? Like, hold on. Maybe if I see, for example, the... can I find myself here somewhere? Hold on. If I can see, like, the age of the server... I actually... No. I have joined it, like, later on. I'm not sure, honestly, how much time I've been coding in Rust. But I don't think it's more than 2 years. I don't think it's more than that. Though I'm not sure. Like... Yeah, I think maybe 2 years. Possibly. Or probably less or more. I have no clue. I really don't remember. But anyway, so the problem is basically that instead of self, we don't want self. We want self output. That was the problem all along. And I was going crazy. There you go. So, bruh. I've started this week. Oh, good luck. Good luck. Though, yeah, so make sure to just go with the Rust book. Make sure to start with that. And then I recommend my own channel, of course, as always. And I recommend another guy that I personally learned from when actually I'm still learning from him a lot of stuff too. I can never spell his name. Rust. There you go, this guy, yeah. John, I don't even know how to spell it. But there you go. He really makes a lot of cool videos if you haven't subscribed to him yet. So yeah, if you have any questions, just drop them, like tell me in streams, or just drop them as comments, or even better, go to my Discord server, ask them, and I can hopefully help you out. Though it probably would be even better if you just joined maybe the Rust server, like the Rust community. You could ask your questions here in Rust questions and answers, and they would surely answer you. Yeah, that's just some little advice. And of course, for sure, I shouldn't even mention that the documentation is your best friend, and of course the compiler is also your best friend. So yeah. All right. Anyway, so that was the problem. Instead of self, I should have said self output. That's the type that I want. Bruh. Like all of that time just because of the stupid thing that I've done here. Forgot. So, but there you go. So that's how you do it. That's basically how you do it. A matrix multiplication in all of its greatness. So anyways, anyways, like the other thing that we could basically make this a bit nicer. Instead of saying dot product, it would be nice if we could just say row into iter dot 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 column into iter, right? So for that we could maybe make a blanket implementation. So how we could do this? Well, why does this cannot move out of what? Oh, I see. Well, I mean, we could just clone it, I guess, right? Okay, let's make sure this actually compiles though. There you go. Cool. So the other thing that I want to say is, I actually forgot. Yeah, I should probably take a break at this point. Yeah, we wanted to make the blanket implementation of dot instead of making it a free function, I guess that's called. Anyways, let's just impl. So we're gonna implement, well, first we actually gotta make a trait. So trait, let's call it dot product. So dot, and it's gonna have RHS, just like add, you know, RHS equal to self by default, and then we could say fn. It would basically have one, or declare one function called dot, which takes self and RHS and RHS, right? And gives back a scalar, right? Now the problem is what scalar would be. Well, I guess we could just we could either make it generic here, or maybe better put it here, I think. But anyways, so that's basically it for that. Let me just get back the AI to help us out here, I guess, if it can. I don't know if it would be able to. Impl dot for row vector. Not really. For any iterator, I think, or isn't it? For any iterator. For iterator. What's going on here? T iterator item equal F64 for T. Okay. Fn dots. Impl has stricter requirements than traits. Label definition of dots from traits. Mismatch types label expected type parameter scalar found F64. Well, this is crazy. What is happening here? Okay. Missing dots. Can it implement it? Implement missing members. Great. Now maybe we could do this. No. Mismatch types. Let's try to compile this and let's see. Expected type parameter. So mismatch types, expected scalar because of return type. Found F64. This is stupid. Right. Impl T for any iterator item T. Impl. What? This is confusing. Did I just forget how to make an... This is crazy. Iterator item t. Dot product equals itself. But why this doesn't work? I mean, it doesn't work with this. Yeah, it doesn't seem like it. Either way, I guess we could just say for now, this, would that work? Yeah, it does. So let's impl t, some n here, const n new size, and the dot product self into iter, I guess. And this is basically t here. Remove this guy. And let's just give that. Bruh, I'm confused right now. Anyways, there's no need. I don't know. My brain is melted right now. Generics. So there you go. Is there anything that I'd like else to do? Or is there any kind of questions or something like that? Let me know. Yeah, let's go back and see if there's anything interesting that we could implement that is very simple, because right now I'm just too tired. Row addition, that is adding a row to another. Yeah, we could do that, but linear equations. Yeah, from now on it just becomes crazy. Linear transformations. Though we could make like a solve function for linear equations and stuff. Right now we're entering the stuff of graphics programming. Yeah, transforming spaces and stuff like that. Square matrix. Yeah, the other thing that I wanted to implement after the multiplication is the multiplicative identity. This should be pretty simple. Invertible matrix and its inverse. Ooh. Well, invert is another story. Definite matrix. Yeah, I should probably read this off camera. Anyways. So, what we should do now. Let's implement the multiplicative identity. And I think that should be it for this stream. How much time we have been streaming for? 2 hours, okay. Alright, so let's implement the multiplicative identity. Multiplicative identity. As you've noticed, the AI can only be as good, you know. Like you always need a human to go besides it. So let's see if it does it. So implement one, yeah, we need to just import that guy. Use numtrace1, yeah. For square matrix, good, because it only applies for square matrix. Where scalar 0, 1, I don't think you need 0. Yeah, you do actually. Yeah, I see. This is for scalar, yeah. Plus add, output equals scalar. Why add? Yeah, because you need that for 0. And multiply, because you need that for 1. And clone. Why clone? I don't think you need clone here. Oopsies. Oh, it's actually needed by 1 and 0 and stuff. Well, fine. I don't know why that's the case. It's stupid. But you do. Yeah, as you can see. Anyways, so self-generate, great, row index, column index. If row index equal column index, which means we are in the diagonal, then we give it a 1, otherwise we give it a 0. Pretty simple stuff. Yeah, great, lovely. So that's basically it to get the multiplicative identity. So yeah, and I think that's it for today's video. Maybe we have implemented a lot of crazy stuff. I guess I'm gonna share this. Yeah, fine, let's share it on GitHub if anyone wants to mess with it, I guess. Let's see. Yeah, I'm going to share after the stream is done, and I'm gonna put the link on my Discord server and maybe in the comment section after I've done that. And yeah, that was it for this live stream. That was a lot of fun and also a lot of frustration. That was it for this stream, and see you later. Goodbye, everyone.